All right. No. Stop it. Sorry. All right. So uh, we're going to keep playing around with um, plots and everything else. So there may be what we're actually going to look at and try to compare today is so I had you count the length of a sequence for the um, ensemble transcripts and also um, the output from transdecoder, right? So I had y'all do that last week as kind of just playing around with this, playing around with graphing histograms and things like that. But today we didn't necessarily directly compare those two distributions. So today we're going to spend some time um, really doing that. So I'm going to start writing out a script. Basically, what I'm going to do is just write out a script that's going to um, read in those data, draw graphs that can compare those two data together, at least visualize differences between the two. Um, so that's what I'm going to do today, and kind of just explain whatever I'm doing, especially if it's something that I'm new, something that's new. So first I need to make sure that this is actually this. I'm going to make a new script. I'm going to save this script, and it needs to be in um, wherever all my data is stored at. So I have this stuff in my 435 blast. Okay, so I'm going to make it a one variable that's called um, ensemble. That's going to hang on to my ensemble data, ensemble link data, just so I can differentiate between the two. Remember, there's no header in this, and it is separated by tabs. Okay, but remember, there's no header, so I'm going to add header. Or I'm going to at least change the names of my headers. Okay. So I'll go ahead and just plot this one out. I have a very bad habit, right? So as a coder, I have a very bad habit of not commenting out my scripts, and I don't comment them out um, because I kind of know what my script is doing. I have a pretty good idea about what it's doing, so I don't typically nobody ever sees what I do, so I don't comment them out very well. It doesn't mean you should, right? Just because I do things doesn't mean I should do things. But either way, so I'm going to add a couple of comments to this. So this is storing um, ensemble link data. Ensemble. So you can always comment stuff. So comments, right? Anything after a hash, um, the computer, your processors won't read. So we can read them. It's visible to us by eye, but it's not visible to computer. So this is just kind of how you comment things. And every script you should make should be reasonably commented out, especially if somebody else is going to be looking at it. They need to be able to know what you're going to do. And there is a growing trend to release all your scripts and release all your data. So they need to be commented in a way that the community can read at least what functions are doing, what they're supposed to be doing if they don't necessarily get the details. Setting my X and Y. So I'm just going to make this, I think this is just going to be a distribution, so it's going to be a histogram. So I just need to define my x-axis, log 10 of length, and geom, so this is a histogram. bins 40 fill equals red. So it's going to be red and color the lines will be black. Save that, make sure it actually will work. Link plot. Something done wrong. What I do, sap equals. All right, so there's my histogram of the log transform data of the length of a transcript from ensemble. So I'm going to do the same thing. I'm going to write it up here. I'm going to keep my plots at the bottom, and then just write in my code to read in the not the ensemble but the trans decoder links. I'm just going to name that trans. What is this called? What file is it called? Ensemble links trans. This is just the file that I named. You don't have this file. It's just the file that I named that's storing all of my trans decoder CDS links. This also doesn't have a header, but it is set by path. Okay, same thing. I need a name, change my names. I'm just going to copy this line and then change ensemble to trans. So and now I have my next plot. So I'm going to draw out my trans plot. Again, I'm just going to copy all this stuff. It's the same thing. All I'm doing is just changing the data frame, and I may change the data frame that I call, what the figure is called, and change the color. So I'll read in the trans data frame. Everything's fine. I'm going to change this to blue and name it trans. Okay, and so there's the distribution of my transdecoder sequences. My sequences links derived from the transdecoder output, right? Remember, I had y'all do this. I did it myself. Use that script to count the links. It has to be the CDS. If you do this by the AA, it's just going to be 3 times shorter than what the DNA sequences is, just because it's amino acids versus the CDS. So we have to make sure that this is a CDS. And so these individual plots are kind of fine. I mean, we can kind of compare them if we look back and forth, but a couple of things are weird, like the x-axis are on different scales. The y-axes are on different scales. So it's a little bit difficult to directly compare these two plots. So, and it's very difficult. If you haven't ever noticed, whenever we run ggplot, we have to call in one data frame, right? It's very, I had, if you can, I've never been able to figure out how, but you cannot, as far as I'm aware, you cannot read in 2 data frames into ggplot to hope that it works. But we do have these 2 data frames that we can merge together. But to make life a little bit easier, so if we're looking at our trans data frame or our data frame, we just have the transcript name and then the links. But if we wanted to merge this with the ensemble data, we would need to add, we would need to define these rows as either belonging to the trans data, transdecoder data, or the ensemble data. So we can do that. We can modify these data frames. So up here, I'm going to modify this data frame by adding a new column called type or TYP for short, and symbols, ensemble. And so I can define a new column, right, using my $sign. So I can define a new column as I type. It's just going to be one word, that this will just be ensemble, E-N-S-E-M-B-L. Okay. And so whenever I do this, whenever I run this command, I'm just going to run it separately. What it will do is then, so it should modify this data frame. So now that I have a third column and all of my rows are defined as being from the ensemble data. So I'm going to do the same thing. I'm going to define a column also called type for my transdecoder data, and just call it trans. So again, so I know where these data came from. So if I source all of this stuff in, rerun this script, something bad, I named that wrong. That's fine. Okay, so now my trans has a type column and everything, every row gets defined as being from the transdecoder output. So now this is both defined. So we can, again, we can merge these files together. We can merge these two data frames together using this command called rbind. And rbind is fairly easy to use. Let's see if the help menu, I haven't looked at the help menu. Well, I don't need to do it there. I need to do that down here. Once again, complain is going to go. What's happening? All right. So there are two types. So we can combine data frames based off of rows or columns. Either way, if we're going to merge like data on the, let's say the y-axis, all the rows have to be the same, or at least one column of every row has to be the same, or the same column has to be present in both data frames if we're merging based off of rows. And for columns, all columns have to at least have the same name. So we have two data frames, and both data frames have the same column names, right? So transcript, length, and type. So we can merge based off of column names using the rbind. And rbind is fairly easy to use. It's probably harder to make data frames compatible to rbind than using rbind itself. So rbind, all it is just saying data frame 1, data frame 2. So in this case, we'll be ensemble and trans. And so I would need to save this as a new data frame. So I'm going to call this merged links and use the rbind. Again, it's just going to say this will be the first half of the new data frame, and that'll be the second half. So we'll have a bunch of rows that correspond to the ensemble data, and then a bunch of rows that correspond to the transcoder data. I'm going to source that. Hopefully this should pop up. I don't get any errors. And so now I have my new merged links data frame. So I have my transcript, my length, and my type. But if I sort by type, I see the ensemble type. And hopefully I should see my trans type. So as long as my column names are the same, it doesn't necessarily matter what all of my rows are and what all of my data in my rows are. But at least if I want to directly compare these two, I need to have a column that defines what data that row belongs to, especially when we're dealing with distributions and box plots and things like that. So now I've merged all of my data together into one data frame that I can then import into ggplot. So I can directly start comparing my data. So the first one I'll deal with will be a box plot. So we'll do merge box plot. Call it inbox. So my data frame is now merged links AES. So this will be a box plot. I need an X and a Y. So my X will be my type. X is equal to type. And my Y will be equal to log 10 length. Okay. And so this is a geom box plot. I do want to give myself a color. Whenever I define colors, it has to be within this AES function. So this will be fill is equal to type as well. So X is equal to type and fill will be equal to type. So I should be able to color those based off of whether the data came from transdecoder or the ensemble. So now let's see if we get this plot back up. Something has gone terribly wrong. This isn't terrible. This isn't necessarily terrible. So we can see my distribution. So this is the distribution from the ensemble links, and this is the distribution of my transdecoder links. So transdecoder, one thing that transdecoder does is that it gets, by default, it will remove any sequence that's shorter than 100 nucleotides. I think we set it. We set it to 300 amino acids or 100 amino acids, so that's 300 bases. So we won't see any sequence shorter than 300 bases in our transdecoder output, just because we filtered based off of that. But the ensemble is normally distributed, right? We've already seen that before, right? So we don't see anything less than 300 bases, and our ensemble is normally distributed. We'll see links of about 1,000 bases. Some are definitely shorter, some are definitely longer, but all of those links are present. So I was even looking in my ensemble data. So if we look at our ensemble data frame, it's including transcripts that are as short as 3 amino acids long. So it very well could be, it's not necessarily wrong, but it could just be like we're saying this transcript is really just one exon, and this exon is one amino acid long or 3 nucleotides long, whatever. Ensemble's keeping track of all this data, so we do see this normal distribution that we don't see in the transdecoder output. But even this, I don't even know if this is necessarily the best way to present this data, because it really doesn't tell us about where all of our data points are. So I think the histograms are nice because it tells us where the density of data points are at, without taking into consideration means, max, and all that. The box plots are nice because it does tell us about our distribution, but it doesn't necessarily tell us where all of it does tell us where our data points are. So, right, we see a lot of data points in this small 25 percentile group. There are a lot of different data points in here. It's relatively short, a very small window of links, probably 700 bases or something like that. A lot of them are found in here, but either way, it's still not necessarily easy to see. But ggplot does have another function, right? So we have all these different types of ways we can plot data out, based off of this plotting function with a lot of different ggplot functions. And so we'll look at one that's a lot easier to look at least directly comparing distributions to one another. And so that plot is called a density plot. I'm going to call it dens plot. At least my variable we call it dens plot. So let's see, merge lens, my AES. So this is when we do this density plot, it is effectively plotting two histograms together on the same x-axis. So we're just defining the x-axis as the length, log 10 length, and we're not setting a y, but we do want to set a color. We want to be able to distinguish these histograms, because if we just do a log 10 of length, it's going to give us a distribution. We might as well just do it. We'll just see what this looks like by default. Geom, called a density plot, and we'll just see what this looks like by default. Then. Okay, so right, it gives us a density plot. This is in effect a histogram of all of these different data points, but we're not telling ggplot to distinguish between the transdecoder links and the ensemble links. So, but we can do that in our AES function by defining fill is equal to, or we can do a line. We'll do color is equal to height. Let's see if that looks a little bit better. No, that did not work. Something has gone wrong. What did I type in wrong? Because my color, do I want fill? I might be doing this wrong. I need to look at a manual real quick if it will load up. Sorry, it's taking a minute longer than I wanted it to be. Yeah, that's fine. AX color, it's not in the right location. No, it's not within my AES axis. That's my problem. Okay, I think that should be fine. I'm just gonna source this script out real quick. Okay, all right. So now I have lines for this. So now I have my x axis, or sorry, now my densities are colored based off of where the data came from, and so we can kind of already see that there are a lot of data points, right? It's effectively a histogram. This tells us how common points are, or how common points are on the x-axis. So um, a lot of points between less than 1,000 bases, but so it's over 500. That's about 750. So a lot of sequences are between 500 and 700 bases, way more than you'd expect based off of general transcript length found in the genome. So let's see, but this necessarily isn't exactly a very pretty graph. Um, we can make it a little bit better by, instead of defining the color of the line, we'll color it in. So instead of defining that, we'll fill it in based off of the type. But if we fill it in, I think what happens is uh, they will be as dense of a color as they can be, and so it's a little bit hard to see the overlap. So it is colored in. That doesn't look terrible, but we can change the opacity. We can change the transparency of these colors within the geom density function. Okay, let's see. This, I think, so this a variable within the geom density is called alpha. And alpha typically describes how opaque or how transparent you want a color to be. So I'll just save that real quick. Okay, and so now these colors are a little more transparent. We can see where they overlap. We can see where the ensemble data overlaps with the transdecoder output. Right, so these density plots are becoming a little bit more common over the past 5 or 10 years in the scientific literature to express and present data. These density plots have become a little more common. They're nice to look at. They are very aesthetically pleasing. Um, and it's nice. So my x-axis is already defined. I did this earlier today, playing around with stuff. My x-axis kind of wasn't my best, but we do start at 0 and end at 5. So this is a pretty nice plot. I guess the last thing that we'll do is we can use statistics. So right, I learned R initially as a stats package. And so there are a lot of built-in stats tests we can do. And one of those stats tests is comparing distributions. Um, and that stats test, you may have heard of it at least. You may not have necessarily played with it, but you might have at least heard of a t-test. And so a t-test is a statistical test that asks, is the mean of two different distributions the same or not? And so we can do that. It's already built in as t-test. And so I would just define as, say, my links. So my links I'm comparing the distribution of my links. So I will do log 10. But if I want, and when I run a t-dot test, I have to define uh, each data source as a vector. So I already have this labeled out. I already have these vectors in my ensemble, in my trans data frames. I just have to pull out those individual vectors. So first of all, I'm going to do log 10 this to normalize and make this more comparable. Ensemble dollar length, comma, close that, and then log 10 trans dollar length. Okay. And so what it's going to do is it's going to look at all these numbers. It's going to look at the distribution, look at standard deviation, and tell us if these distributions are the same or not. And so we see this a lot with, I see this a lot with really big data frames. So remember, we have 68,000 points in the ensemble data and 74,000 points in the trans decoder data. So usually just by the amount of data alone, it's very easy to detect differences, whether or not they're real or not. So how different they are can be defined or described by this p-value. And so a p-value, right? So that's statistical significance. It's basically saying, it's asking, what are the chances these two distributions are different by chance? And so a p-value of less than 0.05 is saying there is a 5% chance that these two distributions are different based off of chance alone. But what this is saying is that our p-value is effectively zero. It's 2.2 times 10 to the negative 16th. It's the smallest number that R can make effectively. So we have 2.2 with 16 zeros in front of it. So it's a very, very small number. These are definitely different distributions, right? But even a graph won't say that these are differences. We usually have to use some kind of stat test to define and decide whether these distributions are different. So if I were to present this graph, I would also present the result of this t-test to say, yeah, my p-value is really, 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 really small. But if my p-value were like 0.5 or 0.1, then it's basically saying there's a 10% chance or there's a 50% chance that these two distributions are different. If there's a 50% chance by chance, they're not different. It's basically saying they're not different. And so you can kind of decide differences based off of that. So if you have a 0.5 t-test or p-value, they're probably not different. 0.1, probably not different. 0.05, they may be different, but definitely less than 0.01, 0.001. They're probably really, really different. But yeah, so I'll probably do one more plotting trick on Friday, and then next week we'll start doing some differential sequence analysis. So like differential expression. So we'll compare. I made each of y'all do an expression analysis on whether it's a liver sample or a kidney sample. And so we'll compare those two expression distributions next week and play around with differential expression analyses using R. We'll have to import a new package to do all of that stuff with, but it should be interesting. All right, but I'm going to call it here for today.